Hello, class. This is Mr. Hart. And in this podcast, we want to continue our discussion of electromagnetic waves or light. And specifically, we want to talk about some of the properties of light, including its speed, energy, and things like that. Okay. But let's start with a property of light you probably all are aware of. Okay. You all know that light is very, very fast. Okay. And that it travels at a constant speed. Okay. So you've probably heard that there's the speed of light, okay? It's actually a constant value that we know in meters per second, okay? So we call it the letter C, okay? So C, we usually use V, but because it's constant, we give it its own value, okay? So the constant value, C, is the speed of light, and it's equal to 3 times 10 to the 8th meters per second, okay? That's really, 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 really fast, okay? It's fast enough to circle the Earth 7 times, I believe, in 1 second. Okay, it's fast enough to get from here to the sun in about 8 minutes. Okay, which is billions of miles away and stuff like that. So it's really, really fast. Okay, you can't watch a light wave, and it's it's something we don't really think about because it just kind of arrives at us instantly. Okay, in comparison, the speed of sound wave is only about 343 meters per second. In the hundreds, when this is in the, hundreds of millions, which is why when you ever watch fireworks, okay, you probably see the firework itself before you see the, or hear the boom, I should say, right? You see the firework, then the sound has to catch up because it's going so much slower, and then you hear the actual boom of the firework, okay? So the point is, it's really, really, really fast, okay? In class, we talk about how it was measured. It was a kind of a cool experiment called the Mickelson Experiment, where they used a rotating mirror to determine how much offset there was from a reflection. We don't have a whole lot of time to go through that. I don't want to make this podcast too long. It takes a couple of minutes to describe. But if you're interested, look up the Mickelson Experiment. It's a really cool experiment for determining how fast the speed of light is. Okay, so if the speed of light is constant, then we have a very useful relationship for determining wavelength and frequency in terms of that speed. Okay, so the speed of light equation looks like this. Okay, C, or the speed of light, is equal to lambda, which hopefully you remember is the wavelength, times the frequency. Okay. Now notice, this is exactly the same as our wave velocity equation. There's nothing different. The only different part of it is that we're using a constant instead of a variable v. Okay, so this may not look like anything cool, but the nice thing is there's only one unknown usually in this equation. If we know the speed of light, and we always do because it's a constant, and we know either the frequency or the wavelength, we can determine the other. Okay, so this is an equation that usually only has one unknown, whereas the other one usually had two. Okay, or we needed two pieces of information. And so this is a really nice relationship because the speed of light is always constant. We can always get frequency from the wavelength and vice versa. Okay, let's do an example problem of that. Okay, in ultraviolet light has a wavelength of 4.10 times 10 to the negative 12th meters. Okay, so really short wavelength. So what would the frequency of that wave be? Okay, well, we know that wavelength, or lambda, equals 4.10 times 10 to the negative 12th meters. And C is still always 3.0 times 10 to the 8th meters per second. Okay? So with that in mind, right, we have enough information to complete the equation. We want to solve for frequency in this case, so we're going to rewrite the equation as frequency equals C over lambda. Okay? Just dividing by lambda on both sides, we get frequency equals C over lambda, which will give us 3 times 10 to the 8th meters per second over 4.10 times 10 to the negative 12th meters. Notice meters will cancel out, which gives us 1 per second, which is a hertz, which is what frequency is measured in. Okay, we put that into our calculator, making sure to put parentheses where needed. Okay, a lot of students forget when you're dividing to make sure you put the whole thing in parentheses. Otherwise, you might get the wrong answer. And when we put that through, you should get that the frequency is a really high number. Okay, it's 7.32 times 10 to the positive 19 hertz. So that's pretty cool. We just determined the frequency of that wave simply from knowing the wavelength and that it was an E and M wave. Okay? Also, we could do the opposite where we have the frequency and we need to know the wavelength. That's also relatively straightforward. We just say, well, in this case, frequency is 8 times 10 to the 14th hertz. Okay? So if C is still 3 times 10 to the 8th meters, we just rewrite the equation as lambda equals C over frequency. Okay? So the wavelength is equal to the speed of light over the frequency, which is 3 times 10 to the 8th meters per second over 8 times 10 to the 14th. 1 per second. So notice seconds will cancel out and we get just meters. Okay? You put that into your calculator. Again, making sure to keep track of parentheses properly. And we get that the wavelength of this wave is 3.75 times 10 to the negative 7 meters. Okay. Again, really, really small. That's a third of a micrometer. Okay, about. Okay. So you couldn't even see it. You would need a microscope to see it. Okay. So really, really small wavelength, really, really high frequency as we expect with light. Okay? So it's pretty cool. We can, again, just use some simple information to figure out everything we need to know about that wave. Okay? All right. Let's talk about energy for a second. Okay? Energy is kind of this thing we've talked about for the whole second semester, right? It's kind of this ability for objects to transfer energy from one thing to another. Okay? Light can heat up objects, okay? It can interact with objects, so it carries some form of energy. And it's its own form of energy, which is what we call light energy, but we want to be able to actually calculate it now. When we were in the energy unit, we're like, oh, we're not going to worry about it right now. Now we want to actually know how much energy there is, okay? And now that we have a good way of calculating frequency, we can now calculate light energy, okay? So this is the key idea. A light wave can carry some amount of energy inside of it, okay, just from its pure oscillation. That amount of energy that it carries is dependent on the frequency of the light wave, okay? So how fast it's oscillating determines how much energy it has. You can kind of think of it like kinematics almost, right, or kinetic energy. Kinetic energy depends on how fast the object is moving. Light depends on how quickly the light is oscillating, okay? So the higher the frequency, the more energy you have. And this makes sense if you go back to the spectrum, the really small wavelengths, like gamma rays, X-rays, they were oscillating back and forth, had huge frequencies, right? The really long ones, like radio waves, really low frequencies, not as much energy. Okay? Same thing with sound, right? Really high-pitched sounds, right? You can hear them really easily without needing a whole lot of equipment, or, you can hear a violin or a piccolo really easily in a band because they carry a lot of energy with them. Because this oscillation is really quick. Whereas a tuba or a bass sound, you need a big subwoofer to get enough energy to actually hear it. Okay. So, point is, light, sound, any type of wave, the frequency is the key component that determines how much energy it has. Okay. So the guy that kind of came up with the equation that describes how much energy there is a man by the name of Max Planck. Okay, you may have heard of him before. He was a quantum physicist back in the early 1900s. Did a lot with quantum mechanics and the behavior of atoms and stuff like that. But one of the things he was able to determine was how much energy was contained in a light wave dependent on its frequency. and he came up with this equation right here. Okay, so the energy of a light wave is equal to what we call Planck's constant. Okay, so energy of a light wave is equal to h, which is Planck's constant. So I can't remember if he named it after himself or someone named it after him for him, but anyways, this is Planck's constant, which we'll look at in just a second, times the frequency. Okay, so again, this shows there's a direct proportionality between the frequency and the energy. More higher frequency you have, more energy you have. Just times it by some constant, and you're good to go. Okay, so relatively straightforward equation. The key here is, what is Planck's constant? Okay, well, again, he determined it, and it's a really, really small number. Okay, so Planck's constant is equal to 6.63 times 10 to the negative 34 joule seconds. Okay, so you times that by the frequency, and you'll get the amount of joules that you have for that light wave. Now, you may say, well, that's really, really small, and it is, but keep in mind, light waves have frequencies that are in the 10 to the 14, 10 to the 28. They can be relatively high frequencies, so you can get quite a bit of energy from a single light wave, which is pretty cool. Okay, so let's do a quick example problem. Okay, so calculate the energy of a photon with a frequency of 8.5 times 10 to the 14 hertz. Okay, well, all we need to do is determine that the frequency is 8.5 times 10 to the 14 hertz. And say, well, we know Planck's constant is, I'm going to have to reference it again, 6.63 times 10 to the negative 34, okay, joule seconds. So the energy is simply timesing those two together. So 8.5, I'm not going to write it again, but 8.5 times 10 to the 14th times 6.63 times 10 to the negative 34th. So you put that into your calculator. Again, just a good habit to either use parentheses or just use the big E notation. But you should get that the energy for that single wave, for just one wave, is 5.64 times 10 to the negative 19 joules. Okay, so that's just for a single photon, and again, that seems really small, but keep in mind how many of these are flowing through the air at any given moment. Okay, they can have quite a bit of energy. Okay, sometimes you'll be given wavelength, but if that's the case, just convert the wavelength to frequency like we had done before, and then put it into this equation. Okay, so the math is relatively straightforward, and we can determine a lot of cool things just from some simple equations. Okay, I want to talk about one more thing really quick for this lesson, and that's about the Doppler effect. So one property of light and sound that we see quite a bit is what's known as the Doppler effect. Okay, now you may have seen this or heard this when you see an ambulance drive by. So it starts with a really high-pitched sound, really annoying high-pitched sound as it's driving by, and then as soon as you leave, you hear this sound, okay? And then the sound's lower after it passes, okay? If you look on YouTube or even just, next time an ambulance is driving by or a policeman's driving by, listen to the siren. You'll hear this dropping of the sound. It'll start really high and go low as it leaves, okay? That's not just some weird coincidence. That's actually a property of waves, okay? Which is what we call the Doppler effect. So the Doppler effect is this change in the pitch of a sound wave or the change in a light wave due to the movement of the source of that sound or light, okay? So if a ambulance is driving by, we hear a certain sound, okay? But as soon as it starts to go away from us, we hear a different sound, okay? That change in perception of sound is the Doppler effect. It could also be light. Something looks like a different color coming towards us and looks like another color leaving us. Okay, we'll get to that in a second. But any change in perception of the sound or light is the Doppler effect. Okay, so why does this occur? If you think about a police siren going down the road, right? it always emits the same sound relative to the driver. The driver, the siren, the car, it doesn't know it's doing anything differently because it's moving. It just always emits the same sound, okay? But we perceive sound by frequency and wavelength, right? So if you have the car or whatever it is driving towards you, even though the policeman is emitting the same spherical sound waves out from the system, because it's moving while it does it, the wavelengths or the peaks of the wave appear closer together because they emit a wavelength, but then they're a little bit closer the next time they emit it, so it looks like they're closer together. So they bunch up on this side, okay? In comparison, as a car leaves or drives away from you, even though they're emitting the same spherical sound, the waves look like they're getting further and further and further apart, okay? Let me demonstrate this with a little simulation. So here's a little simulation of a stationary object emitting sound waves. So it just emits sound waves as, circles or spheres coming out from the source, and it's not moving, okay? So to this person that is perceiving the sound, the wavelengths or the peaks of the wave come at regular intervals, okay? Which is the same as the intervals that the person that's not moving is emitting them, okay? But if that person is moving, let's change this velocity a little bit, okay? Now, even though that person is emitting perfectly spherical sound waves like normal, notice when it gets to the observer, those waves appear to be closer. Those wave peaks appear to be closer. So the perceived sound has a higher pitch than normal, okay? Likewise, once this red dot gets past the observer, okay, now it will switch. So it will have longer distances between peaks because it's moving away from its source. And so the observer will see further away pitches from each other. Okay, they'll see the peaks be further away from each other, have a lower sound to it. Okay? And so that's what we call a Doppler effect. Because the source is moving, we perceive differences in sound. The sound that's being emitted is the same, but we perceive differences in sound. Okay? Now we can do this with light as well. We don't see this as often with light because light moves really fast, but they do this a lot with like stars and galaxies and determining in astronomy how far away something is, okay, and how fast that thing is moving. They do what's called red shift and blue shift, okay? Things that are red shifted, right? Let's say this is planet Earth and this is some star or vice versa. If the thing is red shifted, that means the wavelength is appearing further and further away than it should be, which means that the object is moving away from us. If that's the Earth, that's the star or whatever it is, they're moving apart because the light is getting shifted into the red. It's getting a lower energy, longer wavelength, okay? But if something is blue shifted, that means the Earth and that star are heading towards each other because the light is appearing to be a higher frequency, okay, shorter wavelength, and so those light waves are coming in at a higher frequency than expected, so they're moving towards each other, okay? So we see it a lot in sound. We can perceive it in sound. We can't really perceive it as humans with light, but we use it all the time in astronomy, okay? But again, nothing's changing about the source. It's just a perception difference because of what's moving, okay? So hopefully you learned a lot about light, how to calculate its wavelength and frequency based on the speed of light, how to find the energy of a light wave, and how to understand the Doppler effect. So just make sure you do the homework. Hopefully it all makes sense. Let me know if you have any questions, and thank you for watching.